In the next 15 minutes, I'd like to talk to you about SOLIDWORKS Plastics, what it does, how you can use it in plastic part design, and also share some results of a recent physical correlation study that we did. Plastics indeed make modern life possible. The products are all around us that are injection molded as a manufacturing technique. From your smartphone case, your computer, your child's favorite toy, or a life-saving medical device, even large portions of our cars. They're all made out of plastic. But underneath the shiny plastic surfaces, the intricate features, and the relative design freedom, there's a complex manufacturing process. Let's ask YouTube's engineer guy to explain.
In principle, injection molding is simple. Melt plastic, inject it into a mold, let it cool, and then out pops a plastic product. In reality, injection molding is an intricate and complex process. An injection molding machine has three main parts: the injection unit, the mold, and the clamp. Plastic pellets in the hopper feed into the barrel of the injection unit. Inside the barrel, a screw transports the pellets forward. Heater bands wrapped around the barrel warm up the plastic pellets. As the pellets are moved forward by the screw, they gradually melt and are entirely molten by the time they reach the front of the barrel. Once enough molten plastic is in front of the screw, it rams forward like the plunger of a syringe. In a matter of seconds, the screw injects the molten plastic into the empty part of the mold called the cavity image. The plastic solidifies in under a minute. The mold opens and the part is ejected. The mold then closes and the process repeats.
As we see, the manufacturing process is quite complex, and in the real world it takes a lot of expertise and knowledge to know how to create a tool and actually do the manufacturing. As a designer sitting at my workstation, I'm not always thinking ahead to the manufacturability, and that's where SOLIDWORKS Plastics comes in. SOLIDWORKS Plastics helps me ask and answer a variety of questions. As a manufacturer, I can evaluate different cycle settings or different gate locations, understand what machine requirements I'm going to have, and make sure that I cut steel right the first time to increase my bottom line. But as a designer, that's really who I want to focus on today. I'm more interested in my part quality. What's the aesthetics? Where are the weld lines and sink marks? Is this manufacturable? And is there a way I can design in cost savings up front? And more importantly, as I create more and more complex geometries, can I try something new? I'd like to quickly introduce you to a customer of ours who does a lot of plastic part design, and they faced a lot of common challenges. Echo Group, they create all sorts of customized safety, lighting, and alarm systems, think emergency and construction vehicles. Let's hear from them a little bit about what their challenges were before they started using SOLIDWORKS Plastics.
Before we implemented SOLIDWORKS Plastics, when we did a plastics design, we really had to rely on our tooling partners to give us feedback as to how the tool was going to react to the design we presented.
We kind of had a hope for the best. And sometimes we would get parts that had sink lines in places that we didn't expect. And a lot of times that would result in a negative aesthetic.
Take, for instance, the 12 series light bar base. That's a very big piece of plastic. It's also very complex. And in doing the design, Nick wanted to put in a lot of features that were going to be integral to the success of that product.
12 series base is very unique because what I did on the design part of it was integrate so many features so that we're not having to use a lot of zip ties, a lot of screws, a lot of features that would take up a lot of operator time. So we're integrating that into one solid piece. Plastics was important for multiple reasons. On the base, it was the complexity of the part, making sure it would fill. But on the lens, which is the most visual part, we have to make sure that it fills and there isn't going to be visible flaws such as knit lines or big sink marks that would show up that someone would notice. Plastics allows us to validate that.
It allowed us to run all those what-ifs on these complex parts that we wanted to make part of that base.
Did you notice Nick's double monitors and that huge Series 12 part he was working on? It's an insanely feature-rich part, all sorts of nooks and crannies that make injection molding difficult, and I like that he was trying to integrate more functionality in order to optimize for downstream assembly. But the reliance on the partners for the manufacturing feedback, quote-unquote hoping for the best, mixed with that desire to innovate, this is where new software tools can be very beneficial. Let me switch gears and introduce to you the part we're going to talk about today, And I'm going to pass this around, or you can see on the video here what it looks like. It's not the best cosmetic quality. Here's a few sink marks. You can see there's some out of plane warpage or potato chipping. And overall, it's not the type of part that I would like to receive back. So this is an electronics mounting plate, and let's see how plastics helped us analyze and correlate to this physical part. Let's also talk about what we could do differently from a design standpoint before we even get to manufacturing. Let's start with the most fundamental question: is this part even injection moldable? Will it fill? If it fills, what's it going to look like aesthetically and structurally? And most importantly, can I use that insight, that feedback from the tool to make my design better? When I'm interested in will it fill, I want to understand, are there nooks and crannies that I've designed where the plastic won't get to, but also understand what the cycle time might be for this part, or what kind of manufacturing capabilities I'm going to need. So let's look at the basic filling of this part. And what you're seeing side by side is the physical prototype shot at 4 different volumes. On the right-hand side, you're seeing the SOLIDWORKS Plastics animation of that flow front. The first thing that stands out to me is the correlation, the matching, if you will, between what the digital prototype estimates and on the left-hand side actually running it in a physical mold. As a designer, I'm looking at the right-hand side. Are there nooks and crannies, thin areas where the plastic front can't reach? And what's the overall fill pattern look like? I can also get more quantifiable. And as I look at the design filling, I can understand the time of that flow front as well. So I can see the cycle time here is about 4.1 seconds. I also want to understand what kind of machine. Now here I have an all-rounder 470E. This is the machine that we actually used to create the physical prototype. And this is one I would probably want to read the manual on because it specifies a lot of maximums and minimums. For example, what's the maximum injection pressure this machine can output? What's the max injection volume or weight of the plastic? How much clamping force can it have, which is the reaction of that high-speed, high-pressure injection? I also might want to estimate what my total cycle time is going to be. So we can also get some very fundamental baseline information out from SOLIDWORKS Plastics. For example, my max pressure is a safe 2390 psi. My volume is just below the maximum. My tonnage is going to be okay, and I can estimate my initial cycle time at about 48.6 seconds. Base level information that helps me understand how hard this part is going to be to fill later on. We see that the part can fill just fine and it's going to be safe in my machine. But what will the part look like once it's ejected from the mold? You know, we can see on the physical example, there's actually a lot of warping out of plane that we call potato chipping. On the left-hand side, I have my CAD model, my perfect idealized geometry that I envision in my head and that works in my final assembly. On the right-hand side is the physical prototype, and it's that disparity between the two that really would concern me as a designer. And my goal would be to minimize that disparity between what I want and what I get back. How close am I to my design intent? The first defect that really stands out when I examine the physical part are the sink marks. And we're just talking a few thousandths of an inch, but with my well-polished, shiny mold surface here on the top, I can easily see the sink marks. What's great is SOLIDWORKS Plastics on the top predicted these exact same sink mark magnitudes and locations. So right away I can understand that this part is not going to come back very pretty. The next area I might want to estimate are where the weld lines are going to be, which is where the plastic flow front melds or welds together depending on the angle. And we can get more complicated insights such as what that angle is, but more importantly, this just shows based on my geometry and gate location where the front is going to come together. And this is a little bit harder to see, but if I bump up the contrast and zoom in on the photo, you can see the knit line right above that square knockout. Another piece of feedback I'd want from a cosmetic or structural standpoint is the warpage. On the bottom, you can see the physical, and on the top, you can see the digital prototype. So both estimate pretty much the exact same shape, that out-of-plane potato chipping. Obviously, as a designer, I can easily check if this type of quality is going to be okay as I do my tolerance analysis in my assembly. So we know it doesn't look the best. It's probably not going to meet the form, fit, and function as an electronics mount in the top-level assembly. So can I make it better? That's the whole idea here, right? Is can I take the information we just saw and change my design, and then rerun and get the information difference. So let's make a plastics-driven revision. The first thing I'm going to do is decrease the wall thickness. Now it's a balance. I can't make a wall too thin or else the pressure requirement to fill will be too high, but we saw if I make it too thick, then I get sink marks and warpage. So having a tool like plastics in conjunction with just good rules of thumb when it comes to plastic part design can be infinitely beneficial. I'm also going to take one of the ribs and thin that guy out. I'm going to actually create a hole hollow instead of a solid peg, and then once again decrease the diameter. A few quick changes to the CAD model, and we can rerun in plastics and see what kind of impact our quick design changes had. The first thing I'm going to do is look at those same numbers. Did I make any changes that may have increased the pressure requirements or, violated some of my rules of my machine? And I see that I didn't. In fact, I was able to decrease the volume, decrease the pressure, decrease the reaction force, and also decrease the fill time. So all in all, I'm still within the safety parameters of the machine. Evaluating those sink marks, I can see on the right-hand Rev B that I've pretty much eliminated all the salient ones from the first revision. In fact, now every one is just about 1/1000th of an inch, which, depending on my mold finish, should be acceptable. We can also examine the weld lines, and while weld lines are inevitable, I can validate that, changing this geometry didn't move them to an undesirable location. Or I can change the geometry to make the weld lines come together at a more favorable angle. And of course the warpage we see in the top, that was pretty bad, the first revision. There's a lot of thick areas that were just really changing the cooling times and creating that internal stressing. In Rev B, I've removed that, and so what I'm left with is really just some in-plane shrinkage that's to be expected from the cooling, but not that out-of-plane crazy torsional warping that really would not meet my functional requirements in my assembly. And also, don't forget, we were able to decrease that fill time almost 10%. Now downstream, depending on how many I'm going to produce, this could be a significant time savings. So I can also make sure that design decisions don't lead to extending the cycle time. Overall, we answered some basic questions today. Is it going to fill? Yes, but I also saw it wasn't going to look very good, so I could make it better by using that insight and then validating those design decisions by rerunning the SOLIDWORKS Plastics. Let's return to the electronic controls company. Remember their challenges, and let's see their experience after they started using this tool, SOLIDWORKS Plastics.
By implementing SOLIDWORKS Plastics, we really have been able to pull that instant feedback in-house, reducing the cycle time it used to take while waiting for our partners to give us that very same feedback.
So we use plastics to validate a few different things. One is the design, whether it's manufacturable. We also use it to check features, whether to add or remove or change the dimensions of them.
We were able to optimize our design to say, okay, we can make this out of a single part. It can be this thick of plastic will be strong enough, and the customer wouldn't see any performance degradation, but we can offer this at a lower cost.
One advantage for us in implementing SOLIDWORKS Plastic is the ability to understand how the part is going to behave in tooling. That's extremely important to us, whereas we make optical plastic parts where we have light passing through them. So any deformation in the surface is a tremendous impact on performance. Additionally, we want to make sure that those surfaces are blemish-free of weld lines or nit lines.
So as you've seen, Echo uses a host of SOLIDWORKS products to bring their passion for safety to their customers.
Thanks, Jeremy, and thanks to the Echo Group for sharing their story and some of the benefits that they saw. You know what I think is great is they also use the simulation FEA and the flow simulation to make sure that the products are going to perform safely and optimally out in the field conditions. In summary, SOLIDWORKS Plastics holds a lot of value, and not just for the mold manufacturer and the injection molder, but for the part designer himself, to get that early feedback to avoid the manufacturing difficulties and not wait for that manufacturer partner feedback. We can also improve the part quality, optimize for moldability without sacrificing performance or aesthetics, and overall decrease the time to market. Most critically, I think it increases innovation. It allowed Nick, for example, to create this super wide integrated structure to decrease operation and assembly time. But I also think that as we think of more complex designs and we get more aesthetic with all of our parts and our products, SOLIDWORKS Plastics is more and more becoming a critical part of the designer's toolkit. I want you to think, could SOLIDWORKS Plastics help you on your next project? Thanks a lot, everyone.